power of QAOA. The Leipzig talks are over, so I cannot debate anymore. Okay, you can debate. We have 10 more minutes, still easy.
All right, sounds good. Yes, thanks so much for the introduction. Yeah, so today I'm going to be talking about the QAOA from a bit of a different perspective. This is from kind of the theoretical computer science perspective. And what I'm going to be looking at today is, to what extent does the QAOA offer a speed up over classical methods, and kind of what's the right way that we should measure the speed up, and what's kind of the fair comparison that we should be making to classical algorithms when we're trying to understand the structure of QAOA and its potential for speed ups. So maybe our first inclination as theoretical computer science would be to try to compare the performance of QAOA on approximation problems like MaxCut, and say, take this performance and compare it to the best possible classical algorithms. Right? And if we take this particular standard for establishing a quantum speedup for QAOA, then thus far we have not been able to see any speedups or any worst case performance guarantees for the QAOA over classical algorithms. So for example, if we consider the paradigmatic case of the MaxCut problem, you have some graph and you want to cut the maximum number of edges possible by making a bipartition of the graph. There's a classic result of Gomans and Williamson that says that you can get a 0.878, approximation to the best possible max cut in polynomial time using a very clever SDP algorithm and then a randomized rounding scheme on top of the algorithm. And then in comparison, if you look at the QAOA's performance, for instance, on three regular triangle-free graphs, what Farhi, Goldstone, and Gutman showed in their original paper was that they were able to get 0.6924 approx, or something like this, right? For p equals 1, yes, exactly. Yes, another difficulty here is that the QAOA becomes increasingly difficult to analyze by hand as the p-values increase. So it's usually, a lot of times what's analyzed is a relatively low p-value where you can then make explicit formulas for the QAOA's performance. Okay, all right, so if you take, so this is what happens at p equals 1. Maybe at p equals 2 it might improve. We know that as p increases, the QAOA's performance will get better and better. A natural question is then, well, is there at some point at which the QAOA is going to, say, match the Goldman-Williamson's algorithm's performance, or possibly even exceed it, right? And in this case, for worst case performance guarantees, there have been some results that have been saying that maybe this might not be possible in terms of worst case performance guarantees. And the results are kind of due to two different sorts of perspectives. So the first perspective is a perspective of the unique games conjecture. And the unique games conjecture is, it's a conjecture that some particular problem is NP hard. But it turns out there's a well-known result that says that if the unique games conjecture is true, then it means that getting a 0.878, whatever, plus epsilon approximation is NP hard for any constant epsilon greater than 0, okay? So, of course, the unique games conjecture remains unproven. There's been some partial progress towards resolving some special cases of a unique games conjecture called the 2-to-2 games conjecture that was proven a few years ago. But this is some evidence that maybe the QAOA might not be able to surpass this barrier unless, of course, you believe quantum computers are capable of solving unique games hard or NP hard problems, right? Now, of course, it would be nice to prove such a thing, that the QAOA would never achieve a better performance guarantees. And in the special case of max cut, there actually was a recent result that stated that this is this case. So for instance, there was a recent result of Bravi, Kleisch, Koenig, and Tang just from last October, which said a result that was somewhat of the following form. What they said is that for any p which is less than order log n, then p level QAOA, the best ratio it achieves for max cut is less than or equal to 5/6 plus some quantity which is order 1 over root capital D, and here capital D is just the degree of the graph. So, sorry, let me be a little more precise as to what they said. What they said is that there exists, a family of instances of max cut such that the following holds. So these are particularly kind of difficult instances for the QAOA, and what they showed is that, if you just ramp D up, then the approximation ratio that the QAOA will achieve will be something that looks like something 0.833. Yes?
0.878 unique games for a regular graph?
I don't know off the top of my head, actually. That's a good question. Yes. Yes, okay. So what this was kind of saying was that, okay, if you're really talking about worst case performance guarantees for max cut, again, max cut is not the only optimization problem one cares about, but it's a reasonable and very well studied example, then we actually have some evidence that the QAOA, at least at low depths, will not be able to beat Gomans-Williamson or say the best SDP algorithms. Okay. Yeah, of course.
Well, I think if you look at the Bravi paper, which of course is very nice,
Yeah.
P is less than a small constant times log n.
Yes.
Constant is such that when you look at the subgraphs, they don't cover the whole thing.
Ah, I see.
So, we've always suspected that if you don't see the whole graph, you're not going to be able to.
Yeah, because of locality, of course. Yes.
So it's very important that they're on bounded degree graphs, and P is less than a constant, which goes like 1 over D, I think.
Ah, I see. Got it.
Something like that. So that, yes, but if you make the constant big enough so that you see the whole graph, then they don't have a result.
Sure. Okay, thanks for clarification. Yes, but for constant depth, it certainly is a barrier, definitely. Yeah, exactly. Okay, great. Yeah, so this is kind of, so this was kind of one result, kind of indicating that there could be some limitations to the QAOA. But, this, another kind of natural question you can ask after seeing that result is kind of, is this actually a fair comparison, right? In some sense, you can look at these SDP approximation algorithms of Gomans-Williamson. These are in some sense some of the crown jewels of theoretical computer science, right? Like they're based on, the fact there's even a polynomial time algorithm to solve SDPs in the first place is not obvious, and the choice of these relaxations is particularly clever. On the other hand, we're racing these very fancy SDPs against, something like constant depth quantum circuits, which is an extremely weak model of computation, right? So this is why, sometimes, Eddie in his talks mentions that, there was one particular problem for which QAOA briefly had an advantage over the best possible classical algorithms, and I like Eddie's phrase that the classical SDP people came and then beat up the QAOA, because all ganged up on him in some sense, using kind of these beautiful and rich mathematical tools that have been developed from TCS. So this kind of begs the question, is there a more fair comparison that we can make in order to try to understand the power of the QAOA? And in other words, like, what is the right sort of subset of classical algorithms that are more analogous to what the QAOA is doing? And maybe we can look at those and try to examine with those whether or not there's a computational speedup against those algorithms. And this was precisely the suggestion of a recent paper of Hastings from 2019. And what Hastings suggested is that the right thing to compare to is that we should be comparing to something that he calls local classical algorithms. All right, so what is a local classical algorithm? Let me give you a kind of brief definition of this. Let's say that a p-level, d-dimensional local classical algorithm, let's say for the max cut problem for the moment, though we'll generalize this to more general sorts of optimization problems. It looks something like this. So for each vertex I, we'll give it some value vi, which is lives in some d-dimensional space. Okay, and let's say we initialize the values. The first stage of the algorithm is that we initialize them. We set each vi independently, according to some particular distribution. And then we have another rule, which is that we're going to define like a local update rule. And what the local update rule will be something like this. We'll take each value, each vertex now contains a d-dimensional vector. What we're going to do is we're going to take each vi, and then we'll replace it by some function of vi as well as the vi's of its neighbors in the graph, right? So this is kind of a locally defined update rule. So so I'll call this vj1, vj2, up to vjd, where the ji are the neighbors of I in the graph G. Okay? And then what we'll do is we'll just kind of repeat this local update rule p times. And then what we'll do is at the end, we'll perform some sort of rounding scheme at the end. Because we'll need some way of taking these d-dimensional vectors that we kind of been mixing locally in the graph and then converting them back to plus minus 1 values for the max cut algorithm. Now, the nice thing about this sort of algorithm is that it's quite clearly a classical analog of the QAOA, right? Because what's happening in the QAOA is that, as Eddie was talking about in his talk, is that if you want to evaluate its performance for low values of p, it ends up only the performance of the algorithm only depends on the p local neighborhoods of the graph that it's being defined on. And similarly, the performance of these local classical algorithms is also only a function of the p local neighborhoods as well, because after p iterations of the algorithm, the values of the vi, only depend on the values of the vi assigned to the initial neighbors. Okay. So this is kind of I really like this suggestion because I think it's really capturing a little more of what's going on in the QAOA and a little more of its structure more than, say, an SDP comparison. Okay. Now, the question that Hastings had asked is then, the natural question is then, does the QAOA have a speed up against these local classical algorithms? Now, of course, these local classical algorithms, on the one hand, they're a very restricted class of algorithms. On the other hand, there is some richness there. What distributions do you pick? What rounding scheme do you pick? How do you mix your kind of VIs and as you make these local update rules? Okay, so actually, analyzing this in general is quite hard. But what Hastings actually showed is that he could actually create a one-dimensional local classical algorithm for the max cut problem that at p equals 1 actually outperforms the p equals 1 QAOA on max cut. So this was Hastings' main result in his paper, he actually gave two results. The first one was that there exists a P equals 1, D equals 1 local classical algorithm for max cut, which outperforms P equals 1 QAOA for all D between 2 and 1,000. So there's actually, the regularity of the graph plays a role, except D is 3, 4, 6, or 11. So, and I'll explain why this might have occurred there. And for these, there exists another algorithm. There exists another slightly more complicated algorithm that plugs these holes in D equals 3, 4, 6, and 11. Okay, so what is this saying? Well, this is saying that maybe the story here is it's quite rich. So okay, at P equals 1, what this is saying is that there's actually not a speed up of QAOA against classical algorithms. But I think that it's actually giving rise to a large number of questions to be asked about whether for higher P things like this will still occur, or kind of at what values of P should the QAOA start to pull away. As people were mentioning, at very high values of P, you start to be able to do kind of trotterized adiabatic computation. So maybe there should be some Grover-like speedups or things like this that will occur at higher P. But what's happening at lower P, can be quite different than what one expects at high P. So it's kind of saying that there's some interesting questions here. So I'm going to briefly describe Hastings' algorithm, and after I describe the algorithm, I'll be able to explain why why this exception occurred and kind of the general form of the advantage for max cut that you end up getting out of the algorithm. All right, so what's the algorithm? The algorithm is extremely simple. So what Hastings' algorithm does is it says, okay, initially we're going to set each VI to be uniformly a plus minus 1 value at random. So just at the beginning of the algorithm, I'm just going to pick every spin independently at random. And the expected value of the max cut is, in this case, is a half, right? So the expected number of edges cut is just m over 2, if m's the number of edges, right? Okay, so now what's the update rule going to be? Well, let's define a simple function. I'm going to define a function called fi. Think of this as the force on vertex I that that kind of the neighbors of the vertex are exerting on it, trying to pressure it to flip its sign. So what's fi? I'm going to write it more formally. It's the product of vi and the sum over edges in the graph over adjacent vertices of the vj value. So just to kind of think this out, because I put this on the plus minus 1 basis, if there were an equal number of neighbors that were plus 1 and minus 1, this would be 0, right? So there'd be no force to flip. But on the other hand, if you had more neighbors that were plus 1s than minus 1s, this would be positive valued. So if you were positive value as well, this would give you a positive force that you should be flipping your sign, right? And conversely, if you were already negative and most of your neighbors were positive, then this would be telling you, there would be a negative force. It would kind of be telling you to stay put, right? And the basic algorithm is now the most simple one. The basic algorithm is that you pick a threshold t, pick an integer threshold, and what you're going to do is that you're going to independently and simultaneously, you're going to flip vertex I if the force on it is more than t. Right? This is the entire algorithm. And you just do this in one step. So this is, one thing to note here is that actually all these flips are happening in parallel. It's not like you aren't doing a sweep across the graph where you decide to flip each one in series, but rather this is all happening simultaneously in parallel.
Would it improve if you did it as a sweep?
Yes, it could improve if you do as a sweep, but I don't know if it would get an asymptotic improvement over what they achieved. Okay, so this is the, all right, so are there any questions about the Hastings algorithm? Okay. So the analysis of the algorithm is relatively straightforward. So how do you prove the performance guarantee of this algorithm for a particular threshold t? Well, the analysis is, again, using the fact that this algorithm is local. So you can apply a very QAOA-like analysis to the algorithm. So, the expected value of the cut is, just the sum of the expected value of each edge. So, by linearity, we can just look at what's happening with a single edge ij of the graph. And then what we then do is you say, okay, let's say it's a triangle-free max cut instance. So each of these edges is connected to d-1 disjoint neighbors. Okay. And the intuition here is that if you look at the sum of d-1 plus -1 random variables, this is a random walk, right? So for large D, this thing will be distributed basically as a Gaussian random variable, right? So the sum of the neighbors will be some Gaussian of mean 0, and the variance will be d-1. So the standard deviation, so this is sigma squared. So the standard deviation will be typically of order root d. And when Hastings kind of numerically optimized, when Hastings numerically optimized the algorithm, what he found is that this threshold t basically ends up being some small constant times roughly square root d. Okay? So what does this mean? This means that basically in this algorithm, because these things are Gaussians of standard deviation root d, this means that actually in this update step where you flip some of the vertices, you're going to flip a small constant fraction of the edges, right? So a small constant fraction of the edges will be flipped by the algorithm. Okay? And then if you take a look at, so a small constant fraction, of the vertices will be flipped. Now we want to know kind of what fraction of the time will that actually take our edge ij from being uncut to being cut, right? That's the only question that we need to answer to analyze this algorithm. And here the basic idea for analyzing it is using kind of an idea of conditional independence. So what do I mean by this? Well, let's imagine that in this algorithm you're drawing one Gaussian value here, right, and another Gaussian value here. Let's just say that at the end of the algorithm, this vertex I is at +1. And let's focus on what happens with vertex j in the algorithm. Well, if this Gaussian were drawn such that the force on it was very far from the threshold already, then kind of no matter what happens to vertex I, or no matter what the value of vertex I is relative to j, it won't end up changing the outcome of the flip, right? So there won't be any gain. But the basic intuition is that there's kind of an order 1 over root d probability that on the other hand, there's some very small probability, but something that only goes as 1 over root d, that this value is actually right at the threshold. So if this is the case, then it means that the value of I is then casting the deciding vote in what the value of j will be, right? And if the value of I casts the deciding vote, then that means that the edge will certainly be cut, right? So this is the probability that I casts the deciding vote to flip J. And this is the only case in which this implies that the edge is cut by the algorithm when it kind of would not have been cut in the random assignment. So what this ends up giving you is this ends up giving what you can show very easily is that then the expected number of edges cut will be roughly equal to m times a half plus something that's order 1 over root d. Now, this is actually the precise performance of p equals 1 QAOA when you apply it to d regular max cut as well. It has exactly this 1 over root d performance improvement over random guessing. Now, what Hastings then did is Hastings then numerically optimized the threshold with his computer for each individual value of d, just by brute forcing over all possible assignments to these d local graphs, right? You don't actually have to brute force over 2d plus 1 things, of course, right? All you care about is what's the weight of the vertices here and the weight of the vertices here, how many ones and zeros, or ones and minus ones there are. But that's the essential analysis. And it just happens to so be that the constant you get over this root d is actually higher than the QAOA algorithm, except for these d equals 3, 4, 6, 11 cases. And now I can tell you why these exceptions occurred, right? These exceptions occurred just because summing 3 random variables is not a very good approximation to a Gaussian, it turns out, 3 plus minus 1 variables. Similarly, 3, 4, 6, 11. You kind of get unlucky in the way your discrete approximation to the Gaussian kind of behaves for those kind of exceptional numbers, such that the performance constant, the constant you get here ends up being worse than what's achieved for QAOA. But this is essentially the result. And
So
yes, sure.
You tune the distribution?
Yeah. So okay, good. Okay, yeah. So great. So the question is, how do you fix it? Well, the way that you fix it is with a minor tweak. Instead of drawing each vertex to be a plus minus 1 variable, you draw it uniformly in the interval -1, 1, and then you perform a real mix between it, and now you have a real constant coefficient that you can tune, and then he showed you can tune it like that. Of course, it's a great question what happens with other distributions, but this is one of the first ones you would think of. I think Hastings wrote that explicitly in his paper, that this was just the first one that he tried to fix it, and it happened to work. So, yeah, yes, sure.
Did Hastings discuss the thresholds?
Yes.
Did he teach anything about the algorithm?
Well, Hastings discussed all this analysis that this is, so I should say this entire talk is a survey. So none of this is my work. So Hastings, already discussed this analysis that's order root d, and that the threshold should be some constant times root d. In terms of why it should be the constant that appeared, I'm not sure that there was kind of an insight into this. Though it did is if if you plot what this constant threshold is over time with d, it does actually kind of asymptote, to some limiting value. That's a great question. So, okay, good. All right, so that was Hastings' result. And moreover, he also applied it to another problem, which is the max 3 elin 2 problem, or also max 3 XOR. So his second result was something like for the problem of max 3 XOR, then there's also a p equals 1, d equals 1 local classical algorithm, which kind of beats random guessing by some amount which scales as 1 over d to the 3/4. And this is similar for context. If you take p equals 1 QAOA, then in the original paper where they did this with some kind of instance-independent parameters, then this was the original speed up as well. It also got 1 over d to the 3/4 advantage over random guessing. For p equals 1. Of course, it turns out that if you make a non-local or instance-dependent choice of parameters, then Farhi, Goldstone, and Gutman showed subsequently that this could be improved to 1 over root d. So this is stronger. 1 over root d log d, exactly. Yeah, whereas the best classical is 1 over root d, but it's essentially the same. So what this was showing is that, again, in this framework, it's actually somewhat rich. You're able to reproduce some of the properties that we've seen arising in QAOA, at least at the p equals 1 level and with fairly kind of the most basic forms of QAOA that we can explicitly analyze. So I think that these works are really interesting because they're kind of pointing us towards a lot of fascinating questions. For instance, okay, so far we haven't been able to see any speedups of the QAOA for p equals 1 against these local classical algorithms. Is there some higher value of p at which QAOA pulls ahead? Is there a method of proving lower bounds against these forms of local classical algorithms that can kind of inhibit their performance, but not inhibit the performance of the QAOA, which of course also has the same local structure? So I think that these results are really interesting because they're just pointing to a lot of interesting problems in this area, which we can definitely discuss more over in the discussion period. So, cool, thanks. Great, thanks.
Maybe a quick question, and then
yes.
all this will be discussed during the discussion session. Shall we?
So just as QAOA is reminiscent of algebraic quantum computing, Hastings algorithm is kind of reminiscent of one step of simulated annealing.
Yes, it is, exactly. And at the high p limit, it can reproduce simulated annealing, right? It's rich enough, yeah.
I mean, simulated annealing, one big difference is that it uses a probabilistic update rule. So here it's deterministic. And one
yes.
is that you can get a lot of local minima.
Yes.
This might be a limitation of this.
Yes, so I think that in the most general formulation he wrote in the paper, he did allow probabilistic updates and then probabilistic rounding, in which case, yes, then it does just reproduce kind of simulated annealing in the limit. So this is, in some sense, it's very analogous to what's happening with the QAOA at high P too. Yeah, thanks for pointing that out.
Well, it's more like a spatially distributed version of simulation.
Yes, exactly. It's spatially distributed, but once you go beyond end and you're kind of seeing the whole graph in the algorithm, if you go to very high depths, then I think it can just reproduce simulated annealing.
Okay, so this